So far, we've covered digital signatures, how these fit in with IoT devices, and then certificates, and how they can be used to make an association between public keys and particular identities. I want to try and wrap this up by tying some of these things together and discuss how certificates, specifically X509 certificates, fit within IoT devices. One of the more obvious complaints about X.509 is that it is complex and requires quite a bit of code to process. This is indeed true. However, X.509 support is needed for TLS and DTLS, and a lot of these devices are able to use these protocols. Adding X.509 support for other uses generally doesn't add that much code to the system. Smaller devices, where TLS and DTLS might not be practical, are also probably not talking directly to the internet, but going through some kind of gateway. Generally, there will need to be some kind of pairing between the device and this gateway, and this pairing usually involves shared secrets. The gateway will be a more powerful system that is able to use TLS and any necessary certificates. Another aspect of using X.509, specifically the public key infrastructure, is the size of the root certificate list. As of the 2020.2.40 version of the commonly used CA certificates list, there are 306 certificates, which when encoded in the most compact form are 224,389 bytes. Although this size isn't too significant compared to a modern web browser, it would be a significant amount of space for an IoT device, where the code is often smaller than this. Fortunately, this isn't usually a difficult problem to solve. IoT devices don't generally connect to arbitrary internet sites. If the server or cloud service is known, that service can restrict itself to a smaller number of root certificates, maybe even one, and that certificate instead can be installed within the application or device. One thing that is often overlooked with these certificates is that certificates expire. Part of the block of data associated with a certificate is a validity period. When a certificate expires, it shouldn't be used anymore. In order to handle this, the device will need to be able to periodically update the certificate list. If the list is hard-coded into the application itself will need to be updated. Certificate expiration dates are often on the order of many months or years, so this is usually not a significant problem. On the other hand, if certificates are used to protect firmware, these will either need to not expire or have extremely long expiration times. By its nature, the bootloader needs to be difficult or impossible to update. It would be possible to store the root certificate somewhere else that could be updated later, but this becomes a fairly easy attack vector. An attacker that is able to update the root certificate can replace it with one that they have a private key to, which would allow them to sign whatever firmware images they wished. Normally, certificates are made to expire to reduce risk from private keys that leak. In this case, however, adding an expiration to the certificate would probably result in a less secure system. The last thing I want to cover is the idea of provisioning the devices. This is really a topic for another presentation, but I will cover it a little bit here. It will generally be necessary to get some initial private key into the device through an out-of-band mechanism. For example, it could be written in the factory, and the certificate or public key stored on an external device, which is then delivered to the OEM. This is an area that is ripe for attack, as a single point of attack can compromise a large number of devices. As long as the implementation is careful to never allow the private key to leave the device, or even a protected area of the device, the best an attacker should be able to do is get a list of public keys or certificates for these devices. There may be some loss of privacy here, but it shouldn't be usable to compromise the security of the devices themselves. Beyond that, there are some ways of adding new keys to a device. One way of doing this is to have the device generate its own key pair internally. It then uses this to generate what is known as a certificate signing request. This bundles the information that will appear in a certificate together, but instead of it being directly signed by a trusted entity, it's self-signed. It could also be signed by an existing trusted key or communicated over a channel secured by one of these keys. The trusted entity would then make a signed certificate out of this information and deliver it back to the device. It's also possible to generate the private key off-device, although there is an increased risk of the key being accessed in the process. In conclusion, making IoT devices both self-secure and secure in their networking communication requires the use of digital signatures. Using certificates can help manage these public and private keys, but often trade-offs have to be made, especially with lower-powered devices.